Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. I am super happy to have Sanjana Curtis with us today. Hey, Sanjana.
Hi, everybody. It's great to be here and talk to you.
Well, thank you so much for agreeing to talk about your very lovely APJ letter. Very cool. Very cool. And Sanjana, what's your geolocation? Where are you at these days?
So I'm in Chicago. I'm a postdoc at the University of Chicago in the Astronomy and Astrophysics department.
Very cool. Very cool. How long have you been in?
It's almost a year, actually, a year and a week now.
Okay, so you've been through one full cycle of the seasons.
I sure have. It's been pretty dark for the last 6 months out here, but it's getting better. I saw a cardinal today.
Oh, very good. The snow's all gone. Snow's all gone?
Yeah, absolutely gone, at least down here. Yeah.
Okay. Very cool. Let's see. And it is April 10th of 2023 as we record this. I'm in Phoenix, and we are very definitely starting to get into our summer months. So we were up over 90 yesterday.
Oh my gosh. Okay.
A little warm. All very good. You must be in your office. Is that your office?
I am, yes. It's a shared office with I've kicked my office mate out for a meeting.
Okay. Well, thank you, unnamed office mate. Very nice. And Sanjana, what do you like to do for research?
So I am focused on nucleosynthesis mainly, and also on electromagnetic counterparts of events like core collapse supernovae or mergers of neutron stars or neutron stars and black holes, as we will talk about today. And sort of the idea overall is nuclear astrophysics, multi-messenger astrophysics, bring everybody, theory and observers together to make sense of it all.
Very cool. And that is going to bring us to this very awesome APJ letter. It's open access, people. You can go grab a copy, go get one. Nucleosynthesis in outflows from black hole neutron star merger disk with full GR new RMHD. And Sanjana, take us away.
Yeah, thank you for reading out that a bit of a mouthful of a title. So this is work that I did over the last couple of years with collaborators at Los Alamos National Lab and at North Carolina State. And I want to give a special shout out to Jonah Miller. Jonah Miller is an expert in RMHD and Monte Carlo neutrino transport, and also on disks. And so he is the developer of the code, which is the new Blight code that was used to do the dynamical simulations we've presented.
All right, that's a shout out to Jonah. Very good.
And so the focus of this paper, it's a very compact paper, is on accretion disks that form in the aftermath of black hole neutron star mergers. Now, we're interested in these disks because we're interested in heavy element nucleosynthesis via the rapid neutron capture process. And also the signature of this rapid neutron capture process and the heavy elements that are produced is found in the electromagnetic signal associated with the decay of the heavy elements. So this is the kilonova signal, and recent developments in gravitational wave astrophysics and multi-messenger astrophysics have made it possible for us to observe compact binary mergers and tie them to these kilonovae. And so this is an exciting time to be doing this kind of work. Indeed. And so, for example, if you see a kilonova and you look at where and at what wavelengths emission is happening, it can tell you something about the elements that were produced in the merger. So, for example, if you have a lot of lanthanides produced, which is this group of elements with mass numbers between 140 to 176 or so. Lanthanides have a lot of opacity at short wavelengths, so bluer wavelengths. And so if you observe a kilonova from an event where a lot of lanthanides were produced, that kilonova will tend to have a peak in the redder bands at longer wavelengths because the bluer light has been absorbed by lanthanides. And so if you don't see that, that's also telling you something. If you see a bluer kilonova, it's telling you that the amount of lanthanides present in the ejecta are small.
Okay. Good.
So we can learn things about our process nucleosynthesis, heavy element nucleosynthesis. Right now, it's an exciting time by observing kilonovae. And so we're also interested in understanding what kilonovae from these events should look like from the theory side.
Okay.
So an exciting development recently, well, it's 5 years ago now, has been the AT 2017 GFO kilonova associated with the merger of two neutron stars. And then since then, gravitational waves from black hole neutron star mergers have been observed, but no kilonova associated with a black hole neutron star merger has been observed yet.
Fair enough. Yes.
And so hopefully we will see one of these things. Now, what it should look like, that's one of the questions we were trying to get at by starting to do the nucleosynthesis work associated with these systems. And so these black hole neutron star mergers have not been as well explored as neutron star mergers, I would say. And there's a reason for that because, neutron star binaries, when they merge together, almost every time you have these dynamical ejecta, the system disrupts, there's dynamical ejecta, and there's the potential for a kilonova signal. For black hole neutron star mergers, occasionally the black hole neutron star system will disrupt as it merges together. A lot of the times the black hole will just swallow the neutron star whole. So there's sort of this region of parameter space when you're looking at a black hole neutron star binary, depending upon the mass of the black hole, the mass of the neutron star, the equation of state of the neutron star, and the spin of the black hole. There's a subset of this parameter space where you actually get disruption and mass ejection and a kilonova.
Very cool. Okay.
But we do know that this can happen. And so it's important to kind of have a handle on what is the nucleosynthesis signature? What is the kilonova signature? So here we're focusing on what happens after the merger. And so kind of to begin from the merger itself, as the black hole and the neutron star are approaching each other, the neutron star will get disrupted. And part of this material will be ejected immediately as these tidal dynamical ejecta, mostly concentrated in the equatorial plane. And then the rest of the material settles into a disk around the black hole.
Okay.
And depending upon where you are in the parameter space, the masses of these disks vary. And the way the disks evolve will also vary.
Okay.
But it's important to have a handle on these disks because there's a lot of post-merger mass ejection as well. So in addition to the dynamical ejecta, these post-merger ejecta, these two combined can give you a complete picture of the nucleosynthesis in a system like this.
Okay, I'm with you.
And dynamical ejecta, people have a handle on where they tend to be very neutron rich and produce a lot of lanthanides. Post-merger, things are very messy, a lot more complicated. We need to evolve systems for a very long time to really understand the mass ejection, all of these things. And if that was not enough, there's a lot of important physics going on that involves everything from general relativity, magnetic fields, how the MRI operates, and then neutrino interactions as well.
Yes.
Basically, you need, and that's in the title of this paper, GR, NUR, MHD.
That's how you go. Okay, GR, NUR. Very good. Okay.
So so work has been done on this, on kind of trying to model post-merger outflows, either from neutron star systems or neutron star black hole systems, and to do it with various degrees of approximation to the type of physics that's used. And so some folks have viscous hydrodynamic simulations. You can run those for quite a long time. You can do GRMHD. That tends to be a bit more expensive. You throw in some neutrinos. Now it's even more expensive.
Right.
That's kind of different approaches are needed to sort of explore things for various periods of time, and there's trade-offs here.
Indeed.
And so people have looked at these sort of disks, especially like people like Dan Siegel, Francois Foucault, Oliver Yost, Rodrigo Fernandez. A lot of these folks have done really interesting work. especially simulating things longer term. The special thing about this paper and this code is that not only do we do GRMHD, we also have Monte Carlo neutrino transport.
Okay.
So
Okay.
it's actually solving how neutrinos interact with matter accurately, as accurately as possible.
Right.
And such a simulation with sort of 3D GRMHD and Monte Carlo neutrino transport for black hole neutron star accretion disks has not been done yet. So the only two other works that have been done with this new bytecode, which is now open source, are work on the collapsar disk and a neutron star merger disk.
Okay.
So this is the first 3D GRMHD simulation with Monte Carlo neutrinos and all of that. And so we have some reason to think that if we calculate nucleosynthesis based on this, since neutrinos matter so much for nucleosynthesis, we should have something interesting to say, something that can serve as sort of a benchmark for more approximate methods that people are using, something to compare with.
Very good. Very good.
This disadvantage of doing this type of simulation is that the simulation time tends to be short. And so it's not as short as you might think. Depending upon the disk, we simulate for up to 500 milliseconds, the various disks. But my dream would be to run one of these disks out for a long time.
Okay.
And then really see what kind of outflow components and how they all relate to the properties to the nucleosynthesis.
Okay. Very good.
Okay. Now, right now, we're just focusing on doing the best physics that we can for these disks, and we're doing 4 different ones. So we're trying to kind of cover a parameter space rather than run something very long time.
Okay.
And so we wanted to have 4 disks that kind of go from, a typical disk, a low mass disk to a typical disk to sort of an extreme case of a very massive disk.
Okay.
And so those are the disks 1 through 4 listed in this table here.
Mm-hmm.
And so one thing to notice is that the disks vary in disk mass, but they also vary in sort of the black hole mass and the spin and the entropy and the YE. Now, the reason is that we came up with these disk masses using a certain fitting formula that, given black hole mass and equations of state and spin, et cetera, you can predict sort of the disk mass that you might get.
Okay.
And so we chose our systems carefully to get sort of a range of disk masses here. So then you kind of look at, to set up the initial conditions also, what are the typical entropies and the typical electron fractions that you might find in such disks. And Francois Foucault is an expert on this. And so we consulted him to kind of get a handle on the electron fraction and entropy and things like that. Okay. So we've set up 4 different disks, and we've set them up in a way that we get a range of disk masses. And then the idea is to explore the outflows from these disks, the nucleosynthesis that you get, and then see if there's a correlation between the disk mass and what's going on, between black hole mass and what's going on. It can be a little tricky since those two are a bit tied together. And so I'll get into how things look from disk to disk next. Okay,
and
so
one question, yes. When you run one of these disk models, how long does that take on wall clock time? So are we talking a 1 minute calculation? Are we talking a 1 month calculation?
We're talking a month, yeah.
Okay, a month. Lay it out. Okay, good. Thank you.
Yeah. So most of these are run on Los Alamos supercomputers, and up to a month easily. Okay, so basically, as the disk evolves and accretes, outflows can be launched from the disk through a variety of ways, through a variety of physical reasons. And so you can have thermally driven outflows, you can have magnetically driven outflows, viscous outflows. And so sort of one important thing that we want to understand in future work is to really pin down what's happening exactly in different regions of this outflow. But for now, we just want to look at what is the material that's ejected? What are the properties of that material? What does that mean for nucleosynthesis from black hole neutron star merger disks?
Fair enough.
So we're looking at everything that is unbound according to the Bernoulli parameter at about 250 gravitational radii.
Okay.
And so we find that most of the material that becomes unbound from the system is mildly relativistic. So this is pretty typical of accretion disk material anyway. So 0.1 to 0.2 C tend to be typical speeds of ejecta from accretion disks. And that's what we find as well. And so we can kind of look at our disks themselves in figure 1.
Figure 1. Let's go to figure 1. Let's get a global on this first, and we can drill in as need be.
All right, so these are from top to bottom. It's the least to the most massive disk.
Okay.
And then on the left, you're just looking at sort of in the left half of the figure, the density of the disk, and on the right half, the electron fraction. And then for every disk, on the right is the corresponding outflow and the electron fraction of the outflow.
Okay.
That is shown in this interesting way. So the way it's shown is your electron fraction of the outflow, the unbound material, as a function of angle off of the equator. And so that's the x-axis. And then how that changes with time. That's the y-axis. So
clear here, 0 is the equatorial plane.
Yes. Yes.
Gotcha. I'm with you. Okay.
Exactly. And yeah, so basically you might notice that initially everything in this disk is sitting around, 0.22 in the top panel of YE at about 100 milliseconds. Everything that's being unbound has this average electron fraction value. If we just go to the top one, for example, yes. Yeah. And then, over time, as neutrinos interact with material, that's being unbound, there's this angle-dependent YE structure, electron fraction structure that you find. And so as time goes on, now material that's within about 40 degrees off of the equator is still relatively neutron-rich, but as you go closer and closer to the poles, you're beginning to see the electron fraction rise.
Correct. Okay.
To higher and higher values. So that's kind of how to read this figure. And that behavior from disk to disk is very clearly different here. You can see, in general, the more massive disks, at least the polar region, show a lot higher electron fraction.
Yes.
And then sort of the behavior, since they're all simulated for different periods of time, it's a bit difficult to compare one-to-one, but as you can see, like the y-axis on one of these goes only from 50 to 250, the other one goes from up to 400. It's just the duration of the simulation. So you're just looking at the entire outflow, its character over time. Okay. But yeah, it's hard to compare from here. So we've histogrammed the outflow, right? And then we can kind of take a look at what is going on in our outflows.
Okay. One question. So what is the termination condition for?
Yeah, so it's set to some number of like it's in gravitational time basically.
Yeah,
so
okay.
So that's why from disk to disk it's the same, but because of the black hole mass it's different.
Right, it's the same simulation time, but maybe a different evolutionary state.
Exactly. Yeah.
Gotcha. I'm with you. Thank you. Okay.
Right. So for kind of looking at the properties that are relevant to our process nucleosynthesis, those properties are really the electron fraction, the entropy, and the dynamical time.
Yep.
So that's how quickly is the density changing during nuclear reactions. And so these three things tend to set your average mass of your seed nuclei that are produced for the R process, and then also the neutron to seed ratio. And these two things then together affect largely how the R process is going to go.
Okay.
Okay. So the electron fraction, the closer it is to 0.5, the closer you are to having the same number of protons and neutrons. The lower the electron fraction, the more neutron-rich the ejecta. That's kind of the idea. So the more neutron-rich the ejecta, the more neutrons you have available to capture, and the farther out you can go in making heavier nuclei. Then with the entropy, for example, it's a bit more complicated. It's lower entropies correspond to more massive seed nuclei, but then they also correspond to having a lower neutron to seed ratio. So it can affect our process in different ways. And so these are sort of important relevant quantities that actually people have already explored. Where in this space do you find robust lanthanide synthesis, and where does it begin to fall off? And this lanthanide synthesis, since it's important for the kilonova, that's why we're focusing on the lanthanide synthesis. And it can go very quickly from, having like a solar mass fraction of lanthanides to an order of magnitude lower, depending upon your conditions of electron fraction, dynamical time scale, and entropy. Okay. What does it mean? All this mean for our disks? So that's kind of figure 2 we can get into.
Figure 2.
Okay, so I'm kind of going to begin from the entropy and the dynamical timescale panels. And so this is kind of, there's not a lot of variation from disk to disk as far as the dynamical timescale of the material being unbound goes, and as far as the entropy goes.
Okay.
Occasionally you find something more interesting, like the low mass disk here having a high entropy, high entropy, high YE tail and things like that.
Yes. Okay.
But largely, there's nothing too dramatic that changes from disk to disk as far as entropy and expansion timescale go.
Okay. Yeah.
The main thing that seems to be actually different in interesting ways is this electron fraction distribution of our outflow. And so this is plotted at 5 gigakelvin, which is the relevant temperature for rapid neutron capture nucleosynthesis.
Okay.
And so the 4 disks, disk 1, again, just to remind everybody, is the least massive disk.
Right.
And then disks 2, 3, and 4 become more and more massive as you go. And then we're going from this red histogram to the bluer histograms.
Right.
Now, in general, the tail of the distribution does go up to higher and higher electron fraction as you go more and more massive disks here.
Okay.
But it's a little bit more complicated because you'll see sort of this bimodal structure in the YE. So some of this low YE material is mainly stuff that's being ejected in the equatorial region. Okay. And the stuff that's at higher YE tends to be from the polar regions. We just looked at the figure that kind of showed it to you in a picture. And so the one thing that I can say from looking at this electron fraction distribution is most of the material is above an electron fraction of 0.2. What this means is that you will not get in that material strong R process with sort of like the fission cycling and the very robust pattern that happens. So we are in a region where, depending upon the electron fraction and exactly what the entropy is and exactly what the dynamical timescale is, you can get a range of behavior when it comes to lanthanide synthesis. And so for these typical entropies of 30 kb per baryon and timescales of tens of milliseconds, typically there's a region around an electron fraction 0.25, where you go very quickly from making lanthanides to not making lanthanides in a sufficient solar proportion.
Okay.
So here, already from looking at the electron fraction distribution, we're kind of saying, hey, we're not going to get a full, robust art process.
Right, the whole thing. Mm-hmm.
And we're probably going to find something that's suppressed to various degrees, depending upon the electron fraction distribution, compared to the solar pattern. Okay, so this actually bears out if we look at the mass-weighted abundances that are in figure 3. And so this is for every disk, all of the tracer particles that were in the outflow, their abundances have been mass-weighted and averaged together.
Okay, all right.
So reflecting the total ejecta and what's going on with the total ejecta. An interesting aside is that it was actually a bit challenging to do the nucleosynthesis for this just because of the number of tracer particles in the simulation. So it's 100,000 tracer particles per disk.
Okay.
And we did the nucleosynthesis with this code, the PRISM code, and so there Matt Mumpower and Trevor Sprouse folks are folks who are working with this code, and we consulted them as well as we were running these things.
Good job.
But yeah, 100,000 tracers per disk ran with the PRISM code. And what we found is that basically your expectation based on the electron fraction distribution bears out in the abundance patterns. One might think that you would find the lanthanide synthesis, so this region between 130 and so on, to be more and more suppressed with more massive disks. That would be a neat story, but that's not what's going on. So we do find, the disk 1 and then 2 and 3 kind of do show more and more suppression of these heavy isotopes, but then disk 4 kind of jumps back up.
Yep.
And you can see this reflected in the electron fraction. If you go back and look at it, there's a peak, a very noticeable peak at that lower YE region around 0.2.
Yep. Right.
For disk 4 again, which is shifting sort of our nucleosynthesis back up.
Yes. Okay.
So if you just do sort of the mean YE, this is the pattern that you would expect, and this is what you find. One interesting thing here is also the if you look at the region between 50 to 70, there's synthesis of some zinc and associate nickel and zinc, neutron-rich isotopes of nickel and zinc in for the disks that have a significant component of their outflow sitting at electron fractions closer to 0.4.
Okay. Okay.
So that's kind of interesting just because zinc synthesis is such a mystery, and we've been trying to understand, is it core collapse supernovae, or is it hypernovae, or is it magnetorotational supernovae? Where does the zinc come from in sufficient abundances to explain metal poor star compositions and so on. And so it's interesting to note that there is a component of the ejecta that is doing zinc synthesis in these outflows. So some subsets of black hole neutron star merger disks can produce this type of component.
Very cool.
The sort of the exploration of which physical effect is driving what sort of outflow. This is a next step that we're looking at in order to understand and generalize over a longer term what would happen. The best we can do right now, based on the disks that we have, I think we've skipped a little bit farther ahead. Yes, okay. There we go. So right now, we can at least try to make an estimate for what would happen based on what we have seen in the simulation so far over a longer time when it comes to the outflow.
Okay.
So it looks to be that about 8% of the disk mass is becoming unbound as the disk accretes
Okay.
for all of the disks.
Interesting.
And roughly 8-ish. And if that bears out over a longer term, we have sort of an estimate of that in our table. What is the total ejecta that would produce? And then we also have an upper bound that is coming from, so estimated disk ejecta, that column here is giving you what might happen over a long term in terms of outflows from these disks. And so the lower bound is our 8%, and the upper bound is 40%,
Right.
based on studies from the literature that have run over a longer time, but have employed different physics. So we're kind of just giving a bound on what's possible here.
Very good. Okay.
And so you can kind of see, if you look at the estimated dynamical ejecta and the estimated disk ejecta, that the disk ejecta can be substantial and important for understanding these systems.
Indeed. Okay, cool.
Yeah, and then another thing we've done is give an estimate of the lanthanide fraction of the total ejecta, just to have a number to kind of quantify
Yes.
the nucleosynthesis from these disks, how it would compare to solar abundances.
Okay.
And what that might mean for kilonovae and so on. I'll get into it since it's a lot more complicated in another second. And so one test of nucleosynthesis, in addition to kilonovae, is the composition of metal poor stars.
Yes.
And what we can do, or what Alex G has done in his paper, that the 2019 paper, is produce a lanthanide fraction distribution for metal poor stars. And so now, if we're looking at compact object mergers and we have a lanthanide fraction distribution from those, we have this lanthanide fraction distribution that's observed. You can kind of try to match those two up against each other and see how good we're doing and how much sense it makes and what we might be missing. And so that's the purpose of producing this lanthanide fraction distribution. And we're kind of finding that disk ejecta themselves, since the synthesis of lanthanides is suppressed, they are not going to match up all by themselves with the lanthanide fraction distribution. But once you combine the lanthanides in the dynamical ejecta and the disk ejecta, so sort of that total, the overall ejecta from the merger, then you get pretty close to a typical metal poor star, the typical lanthanide fraction in a metal poor star.
Good. Okay.
So that's nice to see. Again, as we do more exploration of this parameter space and longer simulations, that picture might change, but this is our current estimate that we can provide from sort of state-of-the-art simulations.
Very nice. Very cool.
And then, yes, so this emission equilibrium value of the YE that's computed is, so basically, as the disk evolves, and the way in which weak interactions are occurring and changing the electron fraction of the outflow will also change. So there's your optically thick era, and then there's your optically thin era. Right. And then while a lot of neutrino emission and absorption are important, you're kind of driving the electron fraction of the outflows towards the beta equilibrium value. But later on, as things become optically thin, so this is part of the estimating the outflow over a longer time, later on, your electron fraction will be driven towards the emission equilibrium value, since absorption won't matter so much anymore. The densities are too low. And so that's this estimate of, not only your 8% material becoming unbound over a long time, but the electron fraction of that material, what might that electron fraction be in addition to what we're finding for these initial 500 milliseconds. And so right now, it seems like our electron fraction distribution sits mostly between 0.2 to 0.4. What would happen later on? Right. So that's this estimate of, so right now, this is just for the ejecta that were produced during the course of the simulation. And so we're trying to get a handle on the electron fraction later on.
Right.
And that's the emission equilibrium value of the electron fraction that's been estimated here. And even the emission equilibrium value from disk to disk, which is listed here, 0.39, 0.28, et cetera. So it tends to be above 0.2 at least.
Yeah.
So again, robust R process is not going to happen. The strong R process is not going to happen for this type of ejecta. And then, and then this is again a lower bound. So we actually expect the electron fraction probably would be a little higher than this, and not absolutely at 0.2 or whatever it is.
Right.
Okay, so
cool.
Essentially, yeah, we've taken the simulation we did, we've characterized all the outflow in the nucleosynthesis, and we've made an estimate of what could happen longer term, based on what we found during the course of the simulation. And we do find that in the disk ejecta, the production of elements that are beyond the second peak, the production of elements that are in that lanthanide range, it's suppressed. Yeah. So kind of an exciting part, sort of looking ahead for me, is to get a sense of the kilonova that you might expect from such an event. If we were to observe a black hole neutron star merger and a corresponding kilonova, what would that kilonova look like? And while this nucleosynthesis estimate is important in its own way, when we start thinking of the kilonova, a lot more complication arises, just because there's a structure to the composition of the outflow. In different parts of the outflow, the composition varies, the properties, your velocities, and expansion timescales, all these things vary. And so there's a viewing angle dependence there that's difficult to disentangle with some simple estimate here. But what we can say is that because the dynamical ejecta, which are very lanthanide rich, tend to sit in the equatorial plane, the only other ejecta are the accretion disk ejecta, which are kind of, there's this outflow in the polar region as well. And that outflow tends to be more proton rich and not have a substantial mass fraction of lanthanides. So if we were to view a black hole neutron star merger from the polar direction, if this high YE nature of the outflow persists, we would find a blue kilonova as opposed to a red kilonova.
Yes.
So this is interesting because kind of seeing a blue kilonova from a black hole neutron star merger event, a blue kilonova can very clearly be tied to accretion disk outflows in this case. For neutron star mergers, it's a lot more complicated and messy, with the possibility of having your dynamical shock ejecta and hypermassive neutron stars and so on and so forth. But here, a blue kilonova can very directly be tied to an accretion disk outflow.
Nice. So it's nice.
So that's really cool.
Distinguisher between the two, right? Otherwise,
yeah, exactly. So if we can say something about the kilonova, that's the hope, sort of longer term, looking ahead. But to truly get a sense of the kilonova, again, now you actually have to take into account the morphology and the viewing angle and so on. And so this work will kind of lead towards that. Since we've done these simulations, we're doing more that are on a longer time scale and so on.
Okay, very cool.
And then a brief comment sort of on gamma ray bursts from sort of our collaborators is that based on, there are associations of long gamma ray bursts and kilonova that have been found in the literature, that are being found.
Yes.
Our disks are, even being as massive as they are, cannot provide a long gamma ray burst signal. Just because of the accretion rate and disk mass and how it works out. It's not possible, but maybe there's some other mechanism, for example, through fallback or something like that, the gamma ray burst can be sustained down the line. So yeah, that's kind of a short paper. For the most part, it's basically state-of-the-art simulations that we did. They're short, but they serve as a useful benchmark for other work that is going on in a very exciting field on compact object mergers, on our process nucleosynthesis, and also electromagnetic counterparts.
Awesome. Very cool. Sanjana, thank you so much for walking us through your very lovely APJ letter.
Thank you. This was great.
And I appreciate that you mentioned sort of next steps over the next coming years. And let me push on that. Since one of your dreams was to run those 4-disk simulations to longer times. And
Yes.
we heard that they were actually stopped at a GR timescale of 250. What would you like to run those out to? 2,000, 2,500? Is it even doable on modern computers to run it out as far as one would like?
Yeah, so I would say 1 second is at least quite reasonable.
Okay.
And doable. We won't be able to do all of the disks, but we will be able to do one carefully selected disk. What I would like is to run it out even longer.
Okay.
But at some point we begin to run into, at probably order of 10 seconds or something is going to be very difficult to pull off.
Yeah. Okay. Right.
I think that's where a lot of the other work that's going on will fill in the gaps. Yeah.
Very nice. Very cool. Very cool. Well, thank you once again for walking us through your very lovely article. Thanks.
Thank you.
And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.